The last lecture included a lot of material and ideas that are sort of on the fringes of the classical mechanics. Today we're going to do the stuff that every textbook has, with a little shift. The one thing that we're going to do involves what are called generalized curvilinear coordinates. We're going to introduce that right now instead of waiting for Unit 2 or really Unit 3. So you can get more details on that particular subject by looking ahead at those 2 units which were included in the first part of this textbook. The whole use of that formalism, which is on the board here, all of this stuff right here. So this is the kind of mathematics that you use if you're going to work with relativity, in particular general relativity. So it's a good idea to go ahead and learn mechanics that way. And it's very powerful, and it's very cool. It's very, it simplifies a lot of things, given that you will be forced in physics to use coordinate systems maybe developed based on waves that are not orthogonal. These are called Generalized Curvilinear Coordinates, GCC. So we're going to introduce that today, but we're going to introduce it in connection with the simplest curved coordinate system, which is polar coordinates. 2D polar coordinates. That's enough material of a complexity to pretty well cover all the topics that that particular field of mathematics uses. So let's go ahead here, because the first thing that I want to do is also derive the Lagrangian, and we might talk a little bit about Hamilton equations, but mainly Lagrange for today. The ordinary way. And there are 2 lemmas we need to learn, lemma 1 and lemma 2, that involve partial differential, chain rules. So, nothing too much new on this, except that we have connections to some outside stuff added. And that is, I'm not going to use that one right now, but this one showing lots of links that are interesting. First off, it's coming later. Just to review, this is lecture 8. Just to remind you, we're working with this guy right here. Later on, next lecture, we take on that one. So today it's Irish physics. Okay, we've got lots of diversity in the field of physics, and we're right now centered around the city of Dublin.
Lagrange?
The main thing, starting right here, is to use the chain rules to develop the, well, let's just put it this way. We're figuring out a funny way to say F equal ma. That's what the Lagrange equations do. Newton 2 being written in fancy form. So, if you have a 2-variable function, that's 2 Cartesian variable functions, then a differential of that function, written the way we've got, if we have, whatever functions you're using, you have a f and a g, this can define a coordinate system. And just pick any continuous functions, it's probably going to give you something, a mesh of some kind. It's not going to be necessarily orthogonal, but we're going to pick one that is orthogonal, and that's good old-fashioned polar coordinates. So that's our first deal here. Now I should point out, and that's put right here, that this is, we're going through the Unit 1 of and we're down around Chapter 8, 9, and 10 of 11, and 12 of the review unit. But this particular stuff that we're doing here, I decided to insert, so you won't find that in the actual text. It's looking at these lecture notes in order to get that. In any case, what we want, instead of just a differential of the general function, I want a differential for the radius of the polar coordinate system. And radius is the square root of x squared plus y squared. It's very simple, almost first day of calculus. And theta, the polar angle, also. I'd like to know about these derivatives here. Those derivatives make a matrix. It's called a Jacobian, and that's the key thing that you look for right away when you're working with these generalized coordinates. So I'm going to try to keep these screens coordinated, and in particular, if I go ahead and figure out each of the four, it's a two-dimensional system, so two-squared dimensional matrix, 2 squared equal 4 component Jacobian matrix, simply is cosine minus r sine, then sine theta, r cosine theta. That's it. That's what you look for first. And all of this fancy stuff with the covariant and contravariant vectors is based on looking at this matrix. You got to get this matrix first, and then everything, including our Hamiltonians and Lagrangians that we're going to be building from it, come tumbling out if you know what you're doing. So that's the basic idea of this thing. Now there is some funny notation that you may not be familiar with unless you've been learning about these coordinates. And GCC, it stands for Generalized Curvilinear Coordinate System. And throughout history, I think beginning with Gauss, who's kind of the inventor of all of this, Riemann is a famous mathematician also involved in doing this. I don't know who it was that decided that the notation to be used for a generalized coordinate system was Q. Well, I guess it makes sense because these can be really queer coordinates. So therefore, Q that's the best I can tell you for where the letter Q comes from. But you will find it on almost all of the literature that's what we use. And we'll use it quite consistently when we aren't thinking about any coordinate system in particular. Okay, and here's the other thing that I think is really quite important to keep in mind in all of these equations that we'll be writing from now on, and that is we really don't want to keep having to write this thing. When you want to do a sum over some index, and you've got maybe 5 or 6 of them going here, then you've got sigma, 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 sigma. That takes a lot of wrist motion. We're trying to reduce, keep people from having, what do they call it, carpal syndrome. Here's a way to sort of avoid carpal syndrome, okay? Use what's called the dummy index sum rule. Dummy index m sum. The rule is simple. If an index is repeated on the same side of the equal sign, it's usually over where you're working, but it could be on the other side. If it's just repeated on the same side, not on both sides. If it's on both sides, it doesn't make any sense to sum up all the equations and write them many times. You do the sum on that side of that. In other words, you put in this thing. So we're just going to eliminate that right away. If you see 2 repeated m's in there, get busy and sum them when it comes time to evaluate. In the meantime, you're going to be doing algebraic manipulation with the thing, and then you don't have to pay any attention to that until it comes time to actually evaluate it. Okay, so that's a key thing. Now, how do you make that job a little easier if you're doing a bunch of, we'll have some pretty significant homeworks that have a lot of sums in them. What I do, and maybe the m of the first term is here, but then you got a whole bunch of other terms, and the next m shows up being 20 or so terms down the line here. Draw a line between them, just to indicate, I'm going to sum over those guys, and locate them in your algebra. Okay, this is called visual location. All right. Now, they don't do this in textbooks. Obviously, it's very hard to put a line in, you know, when you're doing type, right? There's nothing does that. Even math type doesn't do that. It's even hard to do it with well, you know, the language that we use. What's not Maxima?
Mathematica.
Math type, and then
Mathematica.
well, no, I'm thinking of the actual language that you use to write equations. I mean, I use it all the time. I can't think of the name of the damn thing. But anyway, even it has a hard time to with that particular. Pardon?
Like latex?
Yeah, latex. Yeah.
Excellent.
Yeah. There are so many varieties of it, you know, and people probably have ways to do that. But anyway, so this is a key thing. This first of all, our cues, but as I say, this indication here is okay with scratch paper, but when it comes time to write your dissertation, you won't have that ability to do that very easily. Okay, so let's get to work here and see there are two lemmas that we really need to do in order to do our fancy mechanics here in these GCC systems. Okay, this key lemma 1 right here is you know, quite crucial. And the idea is pretty simple once we've accepted what we talked about last time, and that was that whenever I do a time derivative, I mean a total time derivative, not parts. I want everything that's going on with this variable to be in the differential derivative that I'm talking about. I put a little dot over it. Okay, so that's our velocity, you see, of that particular dimension. It could be the VW or the SUV. That's back to our two-dimensional system on the freeway, or the pen and the ball when we were doing that. But it could be the pen x-coordinate and then the ball x-coordinate. That would make a four-dimensional system. It would be something over four things, you see. So these indices here, and that's the other thing about this, is that they really annoying, this guy Riemann or Gauss that did this. Most of the time the variables that we work with, particularly the queer variables, they have their indices where an exponent would go. And if you're not used to that, that's really annoying. Okay, you have to get used to that. Can't do anything about that. If you do, nobody's going to be able to read your papers if you put this particular variables on the downside. Later on we will. They're called covariant indices. These are the contravariant. We'll name all that very shortly here. In any case, we would normally just write Vm, unfortunately, is an intensive variable, a contravariant variable, so we put its indices upstairs. More about that later, but in any case, what this is showing us here is that when I take the derivatives here of this, in other words, when I work with not dx, but dx dt, the t's kind of cancel in this fraction here. So the Jacobian matrix that I have to deal with for differentials of coordinates also is the one that I deal with when I talk about the velocities that go with those coordinates. So that's our lemma 1. I mean, it's pretty obvious a lemma, but I decided to make a big fuss about it because there's another one that's not so obvious. It goes with it. And if you don't have these, you don't go to Lagrangian very easily. So, as I say, this Jacobian matrix, this is it right here, does double duty. It does a Jacobian for the coordinates themselves, but it also is a Jacobian matrix for the velocities. So we don't have to have a new matrix for the velocities that go with each of the coordinates in our polar system, or we're making a transformation to the polar system from the Cartesian form. Okay, so let's get that on the board here before we go on. Now, one of the things that I would probably say right away is another way to state this, is you don't need, I'm going to back off that for just a minute, you don't need another Jacobian for velocity. That's, you've got one for the coordinates, it's the same as it is for the velocities. Now, very often, the actual functional definition of a particular queer coordinate system may be really queer. That is, you can't find an easy solution where you get the q's in terms of the x, y's, and the z's that go with the Cartesians. If that's the case, you would kind of be stopped right here, except for something that it turns out to be really neat. If it's the q's derivatives that you're talking about here, or the velocities that you're talking about, you simply invert the Jacobian matrix. That's really cool. This will work no matter what the functional dependence is, whether it's invertible easily analytically or not. If you have to solve a quartic equation in order to write the q's, don't do it. You just go ahead and take what you've got with using the Cartesian side and do the inverse of it. Or vice versa, if for some reason the q's are invertible, then you go back to Cartesian by the matrix inverse. Now most of the stuff that we'll do here right away are 2 by 2s. In fact, today that's all we're going for. Okay. So how do I invert our cosine minus our sine, sine our cosine? How do you invert in general a 2 by 2 matrix? It's so beautifully simple. Switch the diagonals, leave the off diagonals alone, but put a minus sign on it. That's it, except for the determinant. The determinant goes in the denominator. That's just a real quick way to get an inverse in a matrix that everyone should know. Okay, just bingo. You got the inverse, right? And of course, sometimes you write it down. It's always good to check it, right? Because this is the beginning of some calculation, and you make a mistake, not quite getting the inverse right, you're screwed. So these are you know, little hints that I give you to help avoiding getting screwed. And let me get swung up to speed here as well. Okay, if there's anything else I need to say, yeah, there's the thing written out in all story detail, just to remind you about the 2 by 2. Okay? All right. Now, see if there's anything else. Yes, I say always test your inverses. Make sure they give a unit matrix when they're put together. So this is quite an important equation right here. And this is an equation that I like to say it's equivalent to the completeness relation when you're doing bra-kets. You see, bras and kets in quantum mechanics, bra-ket, right? Okay. I'm going to make jokes all about these things. I won't go into that. But anyway, this is what you usually work with when you're just doing calculations with states. But there's this time reversed guy over here, this sort of contra-like, somehow contrarian-like thing called the bra that always has to be with her in order to make an actual number come out of some calculation. Well, the way I look at it is this contra that we're talking about is the index up, and the bra is the index down. So that analogy is worth it. This is called a dual space in mathematics. Okay. And the completeness relation, if you recall, is when you stick a ket bra in between them so that you just get rid of this. You get a sum over that that gives you a number that doesn't reference, in this case, the Cartesian coordinates at all. So this is just another statement that the Jacobian and the Cajobian are inverses of each other. And it's a jokey name, right? I don't think Jacob would like very much that we did this. He's pretty serious about himself. But anyway, this is what's happened. Cajobian is a nice name for whatever it is that you get when you take the inverse of Jacobian. Okay. All right. Let's see if there's anything else here that needs to be brought up. I think that pretty well. Any questions? Because now we got to make use of this stuff. And that involves getting lemma 2. And this is not quite as simple as lemma 1, okay? Because now we're going to be mentioning a double time derivative. Two dots. A total time derivative of x dot. Okay, and x dot is this sum. Okay, and you think, oh, that's no problem. It's just going to be the Jacobian and q dot dot. You'd be leaving this term out if you said that. Okay, because the Jacobian is still usually a function of your position. So when you take a derivative of this thing, you've got to take a derivative of this thing too. So derivative of product is two terms, and that should not be forgotten. Okay, and the polar coordinates very much dependent on where you are in terms of their various ratios to each other. Okay, so in general, this is a result that gives me acceleration of some Cartesian coordinate. In other words, at some point you're going to go around the curve, and you're going to be feeling forces due to going around the curve. It's that simple. It's going to be this guy. Okay? So somehow we have to work that in to our mathematics in order to get an elegant derivation of the Lagrangian version of Newton 2. Okay, so go ahead and say, well, I know how to take a time derivative of anything. I just do a partial derivative with respect to the coordinates times the actual velocity of that particular coordinate. So at some point I got to do a partial derivative of this with respect to each coordinate. So there's a sum here over n. Okay? This j matches that, this m matches that, and it stays still. This is a dummy sum rule that I need to do. And then I can go ahead and put it into a very typical double partial differential that involves this little expression right there. Okay, let's get things up to speed on all of these guys here. And then an important point that comes up right away when we do all of this. And here's where we make use of that thing we made a little bit of a fuss about at the beginning of the last lecture. And that is that I can reverse the order of differentiation in partial derivative land. Okay, so this was on page 15 of lecture 9. So I got to do that. Now, one of the things that you might worry about is, do I have to also include the dependency of the velocity here? I mean, that is the time derivative of the queer coordinate. Is that going to mess me up? And the answer is no, it isn't. These are independent variables. That's the key thing here. Important thing about mechanics is that the coordinates and the derivatives of the coordinates, we call the coordinate velocities, are independent variables in mechanics. I'm able to specify as I throw something where I throw it from, that's the initial position, and how much velocity I gave it from that point. Okay? We do that in our simulations. We click the mouse, and then you drag a little velocity vector, and it takes off in that direction. Nice way to kind of show the independence of those. You have to make an independent choice for all. So given that, I am able to reduce this thing here just to a single partial derivative of x dot. This is x dot right here. Okay? So that leaves us with lemma 2. A time derivative of the Jacobian thing is not so bad after all. It's simply partial x dot with respect to qn. Well, that's an extra thing you have to calculate for mechanics. Okay, the simple Jacobian by itself, if you're just doing curve analysis or geometry, not needed, but we're definitely going to need that. Okay, let's get it on both sides here. The chain rule applied to x dot. Okay, well, we're about halfway there. Let's sort of sum up what it is we have here. Two lemmas, and it's off to the races using these two lemmas for F equal ma, Newton 2. Now I think what I will do is go ahead and bring this screen up to speed with the two lemmas sitting in the places they deserve, prominently at the bottom. And here I'll go ahead and figure out how we handle, well, kinetic energy. That's the quadratic form. It's going to have a GCC, a manifestation, but mainly this guy, F equal ma. Okay, how do you do that in curvilinear coordinates? That's really what we're after here. And this is what we have to do. Now, there are a lot of fine print things that are often left out in descriptions of derivations of this thing. It's pretty sloppy writing in a number of textbooks that I've seen. So I'm trying to avoid that here as much as possible. And one of the things that I'm going to demand is, remember when we talked about the mass matrix, when we were doing the superball stuff? And it was always diagonal. There was just the mass of the ball and the mass of the pen, right? Or the mass of the SUV or the VW, right? We didn't have anything but zeros off diagonal. Here I'm going to say, I'm getting ready here, and I'm willing to have off diagonal M matrices in the Cartesian coordinate system of this thing. Now this could be of many particles. So if I had, 3 particles, and then if I was letting them to run in 3 dimensions, I'd have 9-dimensional sums to do here. And I'm ready to accept that. Now, what in the world do off-diagonal M matrices have? Where does that show up in physics? It shows up when you're actually thinking about a particle running through a lattice. And you run into all kinds of funny side forces. And those are the off-diagonal components that you have to worry about. Effective mass components, effective mass tensor is what you're dealing with. Okay? So there's a place, that's what we do in this building, is worry about things like that. So I think it's good to point out that that's where this would happen. But in order for me to get what I want today, I must have the Cartesian version of the mass matrix be constant. I don't want it to be a function of where you are. Now, if it is a function of what you are, you've got to start over. But we're going to take that thing just to make things the way they are in most derivations of this Lagrangian system. So what we've got here is the F equal ma equation written in Cartesian land, okay? And we're going to try to bring that up to date with GCC, okay? And we're going to do it for polar coordinates in complete gory detail today. And that will, I hope, show you the power, why it is worthwhile to deal with Lagrangian and eventually Hamiltonian equations. So, we have a dummy sum rule right here. That would be over 9 things if there were 3 particles in 3 dimensions. We've only got 2 things, so there's 4 components of our matrix, and then 2 coordinate components. Now, this is the other thing. Remember, we talked early on about how force times distance, that worked out very nicely to be something that described it. If it was a change in coordinates and the force was constant, that was a change in the amount of energy. That would be a work, dW, d work, differential work, okay? But we're saying, if I'm going to dx here, I want to express the thing in terms of, and I use my Jacobian to write the differential, the first differential, in terms of the queer coordinates, the q's. Okay? So, and the other thing is that this f here, if it really is that, in other words, acceleration is that, dot, dot, we've got to put that in. So here's where we hang on our way to make a completely different kind of coordinate system work for us. Now, this is the trick. This is quite a trick when you think about it. And it's just the first of the tricks that Lagrange pulled in order to get himself into where coordinate land. This sum is true term by term. Now what I mean by that is, and I'll just state it right here, it still holds if all of the differentials, because these are independent, you see, I can set them all to 0 except for the one I'm interested in. So therefore, I can just drop having to do the entire sum. I can pick a particular m and just write it like that. That would be what we would call a generalized force right there. And it's a weird kind of Jacobian transformation of the Cartesian force vector. Remember, this is a vector that have 9 components. It's going to have 2 for us today. Okay? So these are also going to have 2 values. They're going to be r and theta. This is going to be x and y. X and y. Okay, x1 and x super 1 and x super 2 is x and y today. But these guys are going to be r and theta, the q's. Okay, so that's the equation that we want to work on. We want to get this thing in a form that is really beautiful. This is what we're really aiming at right here. Okay, so this is a trick, big trick number 1 for the Lagrange derivation, is to write the f equal ma in this funny kind of way. So it's just made of one sum over Cartesian variables for each of the q's, in our case r and theta. So far so good? Okay. This is what we're after. Okay. We have here the generalized GCC force component defined. Okay. And I'll put that up everywhere here. Okay, that's the next thing we need to do right there. And so let's do it. Here's where we do the main trickery of the Lagrange force equations. Okay. And here, this is quite a trick. This is not something for the faint of heart. The physicists sometimes would have a hard time thinking of doing this. Now, what I would ask you to do at a certain point later on in this class, just stop and see if you can remember all the steps that we did today. See if you can rederive Lagrange equations. That's a good exercise, just to get you used to the trickery. The trickery here is just to use the differential relation a dot dot b is equal to the first derivative of a dot b minus a dot b dot. That's just the derivative of a product, right? Turned into a funny equation, right? That's the trick. That's it. Except you got to know what to do it with. And also have some idea why you would do that, okay? So we're going to do it to A, which is a sum over the mass matrix involving the sum K, and then the B is just a Jacobian. And the Jacobian obeys some simple lemmas, which are at the bottom of the screen and at the end there, and that's going to give us Lagrange equations by about here. Okay? So it's really a couple more steps is all we need. All right? Okay. Now, here's where that whereas, the fine print, goes. I can't pull these tricks off unless the Cartesian MJK are constant. Okay, the mass can't be getting bigger or smaller. Okay? That's a big deal when mass gets bigger and smaller, right? MC squared, a lot of energy. Okay, so that's a pretty good thing, but what do you mean by mass? Do you mean effective mass? Do you mean group theoretical mass? Blah, blah, blah. There are all kinds of different kinds of mass. So this could be an annoying thing for other applications. But what we've got here lets me just forget about these constants here as far as these derivatives go. And I do this, it's not going to do anything with that. It's just going to be affecting this and this. And the same thing well, this one has already been spoken for, so we don't need to do anything too much more there. But anyway, to make a long story short, here are the tricks that get played here. First of all, what this boils down to, right here, I've gone too far, once or twice. What this boils down to right here is a total derivative here of the this xj cubed, time derivative of that, okay, this guy right here, let's see if I got that right, yeah, that's fine. I'm going to replace partial x cubed with partial x dot, q dot. And you think, I'm making the equation more complicated here, why do that step? Because what I'm really after here is getting an equation that involves derivatives of kinetic energy. And we almost got it here. I pull this partial derivative off of this thing. I've got an x dot k, x dot j with the mk. That's kinetic energy. So that's to be treasured. And the same thing right here. This is the second lemma. Okay, the time derivative of Jacobian is just a Jacobian, but with velocity in for the coordinate on the top. No change here. Okay, we're almost done now. Okay, all I have to do is meld those together nicely. Okay, and here's just sort of writing that equation here. I'm writing it out with a little v in here for the x dot. So I'm noticing that the partial derivative with respect to the coordinate of v squared over 2, 1/2, that's the kinetic energy velocity factor, okay, is this. Okay, that's the neat thing. And where q may be either q dot or q, depending on whether you're looking at this one or this one. So you end up here with a derivative with respect to velocity of m velocity squared over 2, and here's the coordinate derivative of m times the velocity squared over 2. Kinetic energy in both cases, okay? And that's the Lagrange equation for force, acceleration effect, for Newton 2, okay? So this is a big moment. We should stop and pop champagne bottles and drink from them, maybe, depending on your religion, because this is a big deal to have an equation here that's just about ready to be an equation that's entirely written in terms of kinetic energy in queer coordinates. You now have an equation in queer coordinates. Well, coordinates and velocities of the queer coordinates. Okay. And remember, these coordinates don't have to be orthogonal or anything. It can be wave fronts crossing each other. All right, let's see if there's anything else I need to do here. Just go ahead and rename them. That's it, right there. Now, this is an equation that isn't celebrated enough. We're about to go to the Lagrange equation that you're probably used to if you've taken a good mechanics course, that involves a Lagrangian. But I want to get to one that involves kinetic energy, because it isn't always the truth that I can make a Lagrangian. In order to make a Lagrangian, I have to have a conservative system. It has to be a function of a potential. Okay? The force has to be a function of a potential. All right? That's the second stage. Let's look at what's on the wall up here. In particular, let's look at this. This is what we just derived. I call this the Lagrangian derivative equation. It involves a force component for each of the dimensions in your system. And what it does, and that's I'm going to point this out very quickly here, is it defines a momentum for you at this point. Okay, so we're at this point right now. We have a lot, about twice as much as we've had so far, because we are taking account of something that's feeling a force. All of the other stuff that we've talked about so far, the SUV and the superballs and all those things, they had forces between them, but they didn't have a force on the outside. Nobody outside was changing the momentum. Now it is. Now it is changing. And we're accounting for it fully. And the vector notation for it is this. If you're going to use Gibbs notation. Velocity here, position here. It could be a multi-dimensional position. That doesn't change. Okay. Let's see if there's anything else I need to say. I think we can go for it. This is the next stage. Right here that we're going to be fiddling around with. And that is the conservative system. So things are really a lot simpler if you have a conservative force field. A force that can be expressed as a gradient of a potential. If you have that, then you get what most people call the Lagrange equations. But let me extol the virtues of its humble beginning, that is this thing. I call it the four-wheel drive garbage truck of mechanics. That is, it can go anywhere and take a load of crap. So when you're stuck on a physics problem, because maybe your potential isn't quite what you thought it was, and you want to go back and you actually know the forces, this is the one to go for. It works. It works whether you're in an accelerated frame. You can even throw relativity into it, you name it. This thing can go anywhere. The ones that we're going to come up with, the potential Lagrange equations, the ones that have an L in it, that's very special. And so is the Hamiltonian usually, as we go next step in this development on the lectures that follow next week. Or, we'll look at the calendar in a minute here to tell exactly what's going on. But in any case, this thing right here is definitely to be extolled. But let's go for the one that works the most when you're doing studies of particles and fields and so forth. Well, electric fields. Magnetic field takes some extra work. And the reason the magnetic field takes extra work is that this U here must have no explicit velocity dependence. So this is some more footnotes, whereas fine print that has to go onto the thing that we call the usual Lagrange equation that involves the thing called the usual Lagrangian. Okay, the Lagrangian that's a function of position and velocity, but also has this thing attached to it. This is a funny kind of energy now. Okay, you used to, when you say total energy, you're used to saying T plus U. Kinetic energy plus potential energy. That function has another name. Okay, that function lives in Dublin. That's Hamilton's function, Hamiltonian. Okay, we're back in Paris. This is Lagrangian. Okay, big difference. That is a sign error you do not make. Okay, but in any case, once you do that, you see, once you are able to write the L as T minus U, then you go through and you take this equation and convert it to that. Okay? You put the force inside here as the derivative of Q with a minus sign. That's pretty cool. That's pretty weird. But look at what you get. You get something that really has wonderful symmetry. This is the way I like to write it. Now we've already seen this one. Okay, I'm sorry. We've already seen, let's see if I'm stating it correctly here, the derivative of the kinetic energy. Yeah, that's right. This one, this is our first equation here, where the momentum is the velocity gradient of L, right? We got that by geometry. Okay? What we didn't have was this one. The rate of change of this thing, the momentum, p dot, is a derivative with respect to a coordinate. And in our case, with everything we've studied so far, it didn't matter where you were, the kinetic energy was being conserved. Now it's not. But look at the symmetry here. If I take the dot of this one and just drag it off of the Q and put it on the P, that's this equation. That's the way to remember the Lagrange equations. Both of them. The dot either goes here or it goes there, and it's a P equal a derivative with respect to Q in either case. That's kind of neat. Okay. Well, let's see if there's anything else that I need to comment on. Yeah. If L has no explicit Q dependence, and that's what we've been talking about before, if it doesn't depend on where you are, P dot M, that particular component of momentum, doesn't change. That's a conservation law. That's Lagrange giving you a conservation law for the momentum. That particular momentum, okay, it may be that it's independent of QR, but not of Q phi, or vice versa, which we will talk about today. If it's not a function of Q phi, that means the phi polar angle, you've got a conservation of angular momentum. We're going to show that very quickly in a few minutes. Okay, let's see if there's anything else. All right, now we have to do this task right here. And that is, go ahead and introduce some of the inner workings of the coordinates that make it possible for us to do relativity, but it also makes it possible for us to write very quickly any Lagrangian equation that you can possibly do. Now, this coordinate here is more civilized, shall I say, than GCC. This is called an OCC, a coordinate system. That means orthogonal curvilinear coordinates. And you can see they all meet at right angles except right here. That's a singularity in the Jacobian right there, and the Jacobian. Okay? But everywhere else, to infinity, this is golden. It's just right there. That thing goes berserk. Okay? And when we study complex variables, which will be the last two lectures for this review unit, you'll see some analogies to all of this, the coordinates that you get just by defining a complex function. As you have a real zoo of curvilinear coordinates, but every single one of them is an OCC automatically. And we'll see what that is all about. That's called being analytic function. Okay, so here's our Jacobian, here's our Cajobian. We've already worked that out. The trick is to notice that the columns of this are what we call covariant vectors. These are vectors that slither along the line that they're assigned to. This is an E sub phi, so it's always tangent to the R line, the R equal constant line, in the positive phi direction. I'll make that point more clearly in just a minute. But that is basically what we're what we do. Now the contravariants, the others, they turn out to be gradients. That's these guys right here. They turn out to be gradients of a particular coordinate line equal constant. So those are that's what I need to show in clearer ways. And this is the clearest way I can think of right now, just doing a sketch. But I warn you, these sketches are 2D drawings. Everything in here has got to be in this plane. They kind of look like they curve up out of the plane. They don't. Everything that I'm drawing here, all the curvilinear coordinates are just like this set here. They all lie in the plane of the screen. But here I'm imagining a thing sort of curving away, and you get to feel that this is something that's... What we're talking about would be true for something that did that. But this is a coordinate system I sort of imagine where Q super 1 is 100 on this line and 101 on this line. So it's gone up by 1 unit. In other words, dq has gone up by 1. This is 1. And then this is 1 as well for going from here. This is 200 and that's Q2 equal 201. So this is just some crazy coordinate system I picked out of God knows where. And it has, as a vector, something that's really close to how long it is to 201. And this one right here starts out tangent to this and has a length that's very close to however far it is along a curved line to Q1 equal 101. But basically all of this is based, all this hand waving about here is based on this relation, the first differential relationship. That is E sub 1 and E sub 2, E sub R and sub phi over here are each these vectors here. This particular vector here and this particular component, okay, of that. Those are the two components in X and Y coordinate system of this particular vector. So it's always going along these, and it's approximately, you can see how good it is, approximately the length to the unit change in some scale. There's some scale that makes sense here that would involve radians times about 1.2. Anyway, the other set, the opposite set, this is kind of the bras, the kets, the ones that have their indices up like, well, like the Ion Contra army that had their machetes up in the air, right, after the Sandinistas. I don't know if you guys, I'm telling my age by the fact that I lived through that scandal a long time ago. But these are the Contras, okay, they've got their indices up. These are the, what in quantum mechanics you would call the bras. These are the kets, okay. They're weird because you see what they are the gradients of the coordinates in question, and you can see that down here. Here is E super 1 right here. It doesn't point along that; it points perpendicular to the other coordinate or other coordinate surface. If this were a three-dimensional thing, it is the gradient of this particular coordinate. Whatever, surface, hypersurface, volume, you name it. But here is just a line. Q1 equal 100 has a gradient equal to that at that particular point. And then this one right here is perpendicular to the line that represents Q2 equal 200. Constant Q2, super 2 equal 200. Okay, so those are the definitions of these bizarre curvilinear that work in general. They don't care about whether it's orthonormal or not. This one happens to be orthonormal, but everything that we're saying here is going to be working for that. So the next few slides here, just go through this in piece by piece way, just showing what it is I've said. Each of the covariant vectors that you pull out of the columns of the Jacobian will give you a geometrical unit cell. Unit being sort of in quotes. What it means is if the differentials were actually equal to 1, that's the vector you'd be talking about. It's based on the chain rule. Okay? dr is partial rq1, partial rq2. So taking those components is just what the doctor ordered to make E sub 1 and E sub 2. The contras are quite opposite. They're turned over, you see. This is partial derivative of R respect to Q. This is the inverse of the Jacobian matrix called Jacobian. And we pull off the rows of that to get those components. And that's what's going to be shown next here. But this is the basic idea of the covariance. Is that making sense? Is there anything here that trips your mind and says, I've got to figure out that, I'll figure it out at home. Figure it out right here. We need to get this kind of stuff understood right at the beginning. E1 follows tangent to Q2 equal a constant. Since only Q1 varies in a partial derivative. That's the question you should have asked, is why did this happen, right? That's what a partial derivative is. All the other guys remain constant. Well, I'm looking at that guy. Only one is allowed to vary, so I'll put you on the tangent. Then the fact that that becomes the distance to the next unit of variation, where delta are 1, that's cool. That's really cool. Okay, let's go to the next guy here. The next line here it says, I make a point for physics that these quantities, these covariant quantities, are best used to measure extensive quantities, that is distance, but also velocity, which you could quibble about whether that's extensive or intensive. But anyway. Okay, here's the other side, the contras, the dreaded contras with their red showing very well on this screen. They're not so red in the middle screen, but they're fire engine red down there on that screen. Okay. These are the guys that are normal gradients of their respective, in this case 2, in this case 1, variable equal a constant. So there's Q1, I'm sorry, Q2 equal a constant, 1, there, Q1 equal a constant, 100 right there, Q1 equal 101 there. Same deal here, but this sort of equation is not present here. These are all normal vectors that are being made here. Now, in really advanced mechanics, this is called the tangent space, for good reason. These things are all tangent to the lines that are of importance. And this is called the normal space, also with good reason. All of the vectors are normal to the whatever it is that is being constant. Okay, so the gradients, normals, that's a very important idea. Okay, let's see if there's anything else I need to add to this. Well, yes, there's the bottom line here, basically. The contravariants are really quite useful for force and momentum, and that's what we'll be using them for. Canonical momentum will be covariant momentum. And that takes us back to Dublin. That takes us to the Hamiltonian. That's what the Hamiltonian is going to be making use of, is momentum, not velocity. Okay, velocity, that's Paris, right? Lagrange. All right? Okay. Now, here's what's really cool, is the co's are perpendicular to the contras. Just like orthogonal bras and kets are orthogonal in quantum mechanics, right? That's what that other space is for, basically. It's a secretarial thing, unless you have a orthogonal coordinate system and something that's complex and unorthogonal. These aren't complex necessarily, although we can play that game. We'll do that a little bit later. But this is absolutely a very important axiom, that M and N dot product, N contra and M co, always 1 and 0, depending on whether they are equal or not. It's 0 if they're not. Okay? So that I think is a key thing to remember in this. This is why we're doing this, because we're ready to work with really horrible coordinates that aren't orthogonal. Okay, so just very quickly here, to remind you a little bit of what we just said here, and also bring up what we've already kind of talked about, covariant metric, the actual dot product of M covariant with N covariant, that's this, that can be anything in these coordinates. If these are orthonormal, then this will be a delta function just like this. But this is always a delta function, no matter how screwy the coordinate system is, as long as you're not near a singularity, and that's, of course, a big catch with curvilinear coordinates. They make singularities all over the place. And Rick Hiller thinks that those singularities that you see are the walls that we see in our universe. The walls that have the stuff, and then there's vast regions that has nothing. That's something to think about. In any case, contravariants, they're in general non-zero to each other. It's only when the two get together they make this happen. Okay. Now this is a little bit like Lagrangian, Lagrangian, and Hamiltonian. Okay, but we're not going to make that point because we're playing with the stuff that is more common to our physics and mathematics. Okay, so let's just take a quick look here at how it would be with polar coordinates. That's these guys right here. Here's the Jacobian. There's the columns that give us the covariance. Okay, and then I take the inverse of that and look at the rows, and I get the contravariants. Just write them out. There they are. And then go ahead and notice what the metric is. This is the metric tensor that's so important in relativity. This is the thing that determines length, but here we're using it to determine kinetic energy from velocity. That's the connection that this particular development of the Lagrangian mechanics is taking here. So let's go and look at what happens when you actually use this for something, namely a particle existent in a two-dimensional coordinate system. There's the metric right there. It's just a very simple r squared for the polar angle and a 1 for the thing. So this little dot right here gave us an r squared. Okay. And this is the Lagrangian potential, not specified now. We'll do plenty of that later on. Our oscillator will be our first potential to really look at motions inside the sophomore physics Earth. Okay, but here's where the metric goes. Once you get this metric, it's so easy to get these, take their dot product, bingo. There's your Lagrangian. And you may have a potential that's a function of both r and phi. If it's so, there it sits, and then we're going to be doing the equations that go with that. Okay. Now, what we probably ought to see right away is a thing called Fanatical Momentum. And we know how to get that pretty easily. And there it is, for one coordinate. This particular one is not very surprising. R is kind of an orthogonal-like coordinate. So when I go and use GRR, I put a 1 in for that. Okay, it's only when I get something that's a function of where you are that it gets squirrely. And those are the Coriolis, centripetal, centrifugal, and all that stuff. That's going to fill this space as we finish this lecture. Okay, but this one, no surprise. M, R, dot. And that's radial momentum. Radius is kind of not having any problems right here. But the next one that we'd like to look at here is the momentum. Okay? That is the partial derivative of the Lagrangian with respect to the velocity. So let me put that on all three screens here and remind you of our Lagrange's equations, which is what we're working out here in detail. And this one is a wow. You know, if this is the first time you've seen this, and you've gone through sophomore physics and wondering, what the heck is it? What's this funny inertia, mr squared, blah, blah, blah? Well, that's where it comes from most easily. There's mr squared phi dot. That's angular momentum. Bingo. Really neat. And you see, this is going to work for crazy coordinates, okay? Queer coordinates, right? You're going to be able to get the momentum that goes with that particular coordinate very easily. Okay. So this one is giving you moment of inertia, rotational inertia, angular momentum is the product of that with what we would normally call omega phi dot, angular velocity. Okay? All right. Let's try for some torques and other forces that would come up here. That is what's going. So this is just from the preceding page. Let me jump ahead and actually work those out. Okay? So that's from just what we just did. And here is the next step here. Here, total time derivative, okay? This equation involves total time derivative for each r and phi momenta, okay? Here's p dots. It's the partial of L with respect to r. Here's L. I see an r right there. And remember, partial derivative just treats everything as a constant except r. And I see an r there. Maybe. Depends on whether my potential actually depends on the radius. If it doesn't, I would not have worry about that. Okay? But this one will always be there. And that's a curvilinear effect right there. We're actually taking a partial derivative of the metric coefficient g phi phi, and we're getting this. And then if the potential is a function of r, we get something subtracted from that. Okay? Well, that's another wow. That's a centrifugal force. mr omega squared. Well, mr phi dot squared, that's the same thing. Okay? That's cool. And if it wasn't that, you'd check some arithmetic mistake, you see. Very often you can go and do that. Now this one, if there's nothing in here that's a function of phi, I wouldn't get anything from the kinetics. There's no phis in there. There might be one there. You got a wavy potential, or it goes around the circumference, you're going to have to take that gradient, that partial L with respect to phi. Okay? So, at this point, we're sort of half done with actually writing these equations here. The partials with respect to the coordinates. But also the partials with respect to q dots. But to get the actual, to finish this out, we got just a tiny bit more work to do here. To find p dot directly, and that's what I need to do next here, find a p dot directly from the first Lagrangian, first Lagrange equation, I'm sorry, this thing. This is a time derivative of what we call momentum, p phi, or else pr. We got to take the total time derivative. In other words, now, when I take the derivative, it isn't just look at something that has a t on it. We look at everything. So, as I take a time derivative, total time derivative, I even worry about the m. Does the m not have any? Well, no, we don't have it being anything but a constant. But this guy's got an r in it, so I got to worry about what r dot is. And then this guy, phi dot, I got to worry about it too. All of those give me possible contributions to a total time derivative of that particular quantity. And then, of course, this one too, but that one's easy by comparison. If you look at that, there isn't much going on here when I take to calculate that one. But this one, okay, same thing. Now, it happens here that the P dot for this is just a partial L with respect to phi, and if we don't have any explicit dependence on the potential, I'm golden on that one. This is a conserved quantity. Call it script L or something like that for angular momentum conservation. But the finishing this thing, where I really have to take the time derivative of that, that's the part that gives you a few more terms that you have to worry about. So let's go ahead and do it first on this screen, and then on this screen, and then we're done for the day. But we've got to talk about these. These are not quite so simple as the first half of the analysis of Lagrant Equation. So taking a derivative here of the momentum, actually an explicit expression for it, that's a pretty easy job. Okay, so I will just get mr dot dot for p dot here. Now, if you work out let's see if I've got that right. If I work out, you know, this thing, if I ask the time derivative of that thing, okay, this is what it is. I've got an mr phi dot squared. That was centrifugal force. So after we get this finished here, we actually figure out what r dot dot is. That's the whole story right there. And let me go ahead one step on this one step on this one, and one step on this one to finish the dots. And look at p dot phi right here. That's the non-trivial one. As I go to take the time derivative of this, I get two terms. One of them involving a derivative of this, which gives me the factor of 2, and then r times r dot, that's r squared, being differentiated totally. And then the next one is the derivative of that, r dot, I'm sorry, phi dot, is phi dot dot. Okay, so there are two really important terms right there. And this is the Coriolis effect. Okay, so that again, I say wow, because Coriolis is really kind of a tricky thing to deal with, as I pointed out when we just sort of hand-waved our way through its discussion. This is very quantitative and very simple. It's admittedly only in 2 dimensions, but you'll see when I give you a problem with 3 that it's really quite easy to do all of this and calculate these quantities. Now, we have something to do here, I think, that's really germane at this particular point when our southern friends are having an awful time because of one of these damn things. But what really causes the disaster, shall we say, that a hurricane provides? And I'm going to go ahead and advance this one by maybe one step, and I probably can do it here as well, just to give you a feeling. Because this is an equation, this particular one right here that we just calculated, and let's just assume we don't have any potentials here, we don't need them. We've already got the whole thing moving at some particular value. Now what we're doing here is I'm saying this thing, if I get the m's out of there, divide by r squared, kill that r to get 1r, and forget about that. That's the key factor right there that drives our weather. We're on a rotating globe. It's got a velocity phi dot. The phi dot is this way. Okay, we're looking down from the North Pole at the Earth. It's going like that, right? You go around the thing and the sun rises, right? And then the sun sets, right? Talking like a northerner. Now, if this was by an Australian, we'd have it going the other way. Then we turn other things around as well. Let's just stay up in the north. Okay, we've got phi dot greater than 0, and we've got r dot. Now here's the deal: you get a low pressure area anywhere, and the atmosphere suddenly says, "Hey, there's something going on here. We got to go for it." stuff pushing on us. We've got a low pressure region. Well, when that low pressure region starts to bring the air in, this is the equation telling you what's going to happen to your phi dot. It's going to get dotted again. And it's going to be -2, okay, but this is minus, that's positive, so you're going to get a positive rotation. This is going to make right-handed. Now, I like to use the quantum mechanical view of this thing, and I think I've got that actually written at the bottom there. Might as well put it here too. Deep quantum rule. Flow tries to mimic the external rotation. In other words, reduce the relative velocities. Because relative velocities is like a beat of the waves, and that's high energy. You want to get that. You want to get that low. Nature tries to get that low. So the easy way to remember is which way things are going to be turning due to the rotation of the Earth. They're going to turn in the direction of the rotation. And we'll see that more clearly with these various rotational demos that we'll show later on. But that's really something to know. And the other thing is that this whole system, on the average, moves, if it's not violent like the one that's going on in the Carolinas, it will move with the rotation of the Earth. That is, our weather systems come from the west, pass through, and when they're approaching us here, something out in Oklahoma or Colorado is coming and it's strong, you're going to see a nice warm south wind preceding that storm. When the storm gets here, you're going to see the wind shift, and as it goes away, you're going to feel a nice cool breeze from the north and clear air usually. Okay, so that's just an ordinary weather system. This hurricane is an extreme case of that. Very extreme. I mean, that extreme. Okay, and this is from Ima, the Hurricane Ima. But Florence is actually the same size as that. It's giant. So right now they're getting all of that water off of the ocean coming and dropping in the middle of the state. And I guess the latest count was something like 5 feet of rain. And these are, you know, kind of record-breaking for this country. You go to India or any of the continents that have typhoons, they broke that record a long time ago. And they get them more often. And they're just like we are getting them more often because the water has warmed up. Okay, well, we're right on time almost for this, and this is enough said. I think I've tried to give you the idea that the Lagrangian is a powerful tool. Hamiltonian is too, but very different. It uses covariant quantities. None of this contra stuff. Okay, we'll see you next time.